picture on the top, we have a 60 Hz voltage signal with its fifth harmonic, a 300 Hz signal shown in the red. Now, if both waveforms were to exist in the same power system, the resultant group resembles a picture down below. Although this new signal is still periodic, it is no longer purely sinusoidal. And that is the effect of just one harmonic. If we have multiple harmonics, they will have the ability to completely change the intended signal. Now, let's move on to the definition and some of the causes of harmonics.
AC voltage, like any time domain signal, can be represented mathematically by a summation of different frequency components using the Fourier transform. In North America, voltage supplied to loads is ideally consisted only of a 60 Hz component, the very same frequency it is generated at the source. Since neither the generation nor the consumption of power is perfectly sinusoidal, voltage in power systems is prone to distortions known as harmonics. As noise superimposed on a fundamental component, harmonics add many smaller but faster moving waveforms at integer multiples of the fundamental frequency. Now let's look at some of the causes of harmonics. Harmonics in power systems are mainly caused by nonlinear loads. Although all electrical equipment possesses some kind of nonlinearity, most of the effects can be safely neglected. However, the same cannot be said with loads like transistors, MOSFETs, and transformers. Unlike linear loads, which draw currents either in or out of phase with the supply voltage, nonlinear loads draw currents in abrupt pulses.
Now we will move on to power quality. My name is Rebecca, and I will explain the definition of harmonics and several ways to improve power quality, including use broadband filters, the line reactors, and series active filters. Now I will explain in detail.
Power quality can be viewed as a compatibility factor between power grid and consumers. Common power quality parameters include the continuity of power, harmonic distortion level, and power factor. Continuity of service is the most basic parameter of power quality. As expected, discontinuous current causes many problems to both electrical equipment and power grid. Harmonic distortion level defines the degree of deviation between a harmonic wave from a sinusoidal wave. It is dependent on the power source and the nonlinear load. Power factor is also extremely important when evaluating power quality. It measures the effectiveness of electrical equipment converting current to power output. According to BC Hydro standards, it's recommended to maintain a power factor of 90% lagging to optimize power quality.
Now we already know the definition of harmonic and power quality, but we do not know the relationship between them. So now I will be talking about the effect of harmonic on power quality.
When a sinusoidal voltage is applied to linear load, the current drawn by the load is proportional to the voltage and impedance and follows the envelope of the voltage waveform. Linear loads are loads in which voltage and current flow one another without any distortion to their sinusoidal behavior. Resistive heater, incandescent lamps, and constant speed induction and synchronous motor are examples of linear load. On the other hand, most loads are nonlinear, and the waveforms of their current and voltage are not purely sinusoidal. Waveforms in nonlinear loads are about 60 Hz and contain numerous additional waveforms of their frequencies superimposed upon it. The multiple frequencies are harmonic of the fundamentals. Examples of nonlinear loads are battery charges and variable frequency drives.
Hi, my name is Tyler. I will be talking about the effect of harmonics on electrical systems. I will mainly talk about four following components: motor, transformer, capacitor banks, and cables.
Harmonic current causes audible noise and vibration in a motor due to the frequency deviation. It produces resultant flux between the rotor and the air gap, which causes cogging or slipping in induction motors. The alternating magnetic field contributes to iron losses such as eddy current and hysteresis losses in motor cores. These losses are directly proportional to frequency, which ultimately relates back to harmonics. In conclusion, power losses will increase due to harmonic voltage and currents in different ways. Transformers have similar reactions to motors under harmonic effects. The non-sinusoidal excitation voltage increases current in the magnetic core the same way it does in a motor. Eddy currents are induced by the leakage magnetic field and represents a more serious effect of harmonic loads served by transformers. Eddy current losses increase with respect to the square of the current and square of its frequency. As a result, transformers' operational temperature gets significantly affected and the life expectancy gets reduced. In a power system filled by large voltage and current harmonics, the rated voltage and reactive power are frequently exceeded. Capacitor banks act like a sink, attracting harmonic currents and then become overloaded. The combination of harmonics and capacitor banks equates to a serious power quality problem called harmonic resonance. Resonance exists in a series or parallel. One amplifies voltage and the other amplifies current. In a harmonic-rich environment, both types are present. As a result, the life expectancy of the capacitor banks gets significantly reduced. The flow of current in a cable produces power losses and current distortion. The effective resistance of the cable is proportional with frequency due to skin effect. It is important to make sure a cable is rated for proper current flow, because both fundamental and harmonic current can flow in the conductor simultaneously.
Wow, the harmonics are having so many effects on the power quality, so we're really interested in how to get rid of the harmonics. Actually, there are four main ways of eliminating the harmonics, including using transformers, the separated, oversized neutral conductors, using current limiting reactors, and special meters. So now I will explain in detail.
The most commonly used way of eliminating harmonics is to use different types of transformers. Delta-Y connected transformers could reduce harmonics by shifting the phase by 30 degrees, trapping all the tripling harmonics, in addition to the neutral eliminated even harmonics. YY zigzag connection produces output which is the vector sum of the two phases offset by 120 degrees. Thus, it could also help to eliminate the tripling harmonics, plus the fifth and seventh harmonics. Separated oversized neutral conductors are commonly used in transmission lines to eliminate the neutral harmonics. Since the neutral point is not connected in this type of conductors, there will be no harmonics current generated on the circuit neutrals. However, this would result in an increase in the copper use by 33%, which would significantly increase the cost and size of the transmission lines. Current limiting reactors are widely used in motor circuits since they limit the maximum current flowing in the circuit, which helps to prevent the circuit from overheating and reduce the generation of harmonics. Harmonics could be hardly noticed since standard current meters are only sensitive to 60 Hz current. To better investigate in harmonics, special devices are used to sense current up to the kilohertz range. Different types of filters are then made accordingly to eliminate the harmonics with a specific range. Thank you for watching this video. If you have any question, you can send us an email to the address shown on the screen. Thank you.